Okay, welcome to the channel. Welcome. This is now attempt 5 to record one of these videos. Um, First attempt was almost last week, um, and that was just to get any sort of YouTube video. And now we are on attempt 4 to record, particularly for today. Um, so I'm going to start by motivating the channel. This is the first video. The focus of the channel is just for me to think out loud and publicly. So you know, me posting myself on the internet is embarrassing, and I'm going to use that as like a forcing function to do like a better job of thinking and like taking the things that I'm trying to do more seriously, and as well thinking out loud. That's also going to be a forcing function for higher quality reasoning on my end because I don't know, you think out loud, and it's closer to like interview kind of stuff. You know what I mean? Is like it's just a nicer set of skills to have, is if I want to be able to talk to someone and like I think I have good ideas, I should be able to communicate them. So this is going to be my playground where the only cost is me being embarrassed in theory, um, to work on these things. So today's working session, I guess I need to give context on Vault Chat again as well. Is Vault Chat is this app I built entirely vibe coded with a lot of help from Claude. And what it does is, if you ever saw the videos of Claude Code and Obsidian as a duo, um, it is it's a it's an IDE in a way. But the premise isn't for like code development or anything. It's like for studying and like knowledge. Um, so like the mediums it supports are like it supports code files. There's like a terminal in it. I have a PDF. That's the app in the background right now. PDFs Markdown, and then there's like an agent on the inside that can that can see all the mediums and help me interact with them, internalize them, voice mode. Hopefully we'll use that today of like richer richer discussion than typing and reading. It's just a bit we want to make things seamless. Um, so we have that. Previously, this week, I had Vault Chat try to reproduce the coconut paper from Meta. It failed, and it cost me about $80. I don't want it. Gave me a diagnosis of why it failed, um, but I don't trust it. So I'm not gonna make another $80 bet on whether or not um, AI can do like the little things necessary to actually fully to finish reproducing the paper. So today there's sort of a few things going on. I think we're on 3 things now. In last video I said 2, but you don't have that video. So first one, and let's rank them in priority. First priority is looking at the artifacts of the run. Is I had Vault Chat also produce for me a a deliverable in sort of like story form of like, what the reproduction is, why it failed, had to dumb it down for my level of understanding. And internalizing that, discussing that, understanding that, that's our first goal. Our second goal is behind me is the looking at the actual paper. I haven't done that. And then our third goal is I'm blanking on it. It has something to do with Vault Chat. Oh, I was thinking about like sort of like yeah, it's like small things of like the design of Vault Chat, like being like a vibe coded app. There's some things going on behind the scenes that I sort of just like trust were built well, and I think I might want to like dial in on those because I think I can systematically make Vault Chat better at completing missions and like these longer horizon tasks, like reproducing a paper. Um, so instead of just like the my traditional flow has been, try to do something, it doesn't work, and then have it leave a note and then have Claude fix it. Like do have Claude reason over why it failed, fix it. And that I mean that's gotten the app like fairly far. Um, but I just think I can make it better. You know what I mean? So I might do that. That's like the last thing that we care about. Number one thing we care about is internalizing the report on the failure, understanding the story of reproducing it, maybe inspecting the code. And second, if we have the time, if we manage for it, to also look at the paper. So let's get started. I have the paper opened. I had started, so I had done this in my previous recording attempt. Is I was sort of looking over this. So I'm gonna jump into actually talking to David about it. David is the name of the voice in VaultChat. Um, I haven't done too much thinking about my naming conventions. VaultChat is the app. David. VaultChat is also the name of the general agent. David is the name of the voice. Um, so I want to talk to David about this diagram and the paper in general. So related work, chain of thought reasoning, latent reasoning for LLMs, coconut chain of thought. Yeah. You see, and I just don't have time. We're really trying to like do things differently, you know? I'm making like a various number of bets of I would like to be in this space and not work hard, you know? That's not true. Um, but I think deep learning is cool. I think solving AGI, cool. Or, betting or early bets. I'm a big fan of like local models. Unfortunately, I can't afford them, at least good ones. Um, so I think AGI should be local. I think I should have my own AGI, and that it should be fast. That's another thing. Um, I think tokens per second underrated. Um, so how can we do this well? I want to internalize this paper. I don't want to read line for line. A conversation is a pretty read-rich medium. We have access to that. VaultChat can read the PDF. It's using Gemini 2.5 for voice mode in the background. Special tokens. Okay, I thought about this before. It's like, yeah, BOT and EOT, beginning of thought, end of thought, are going to just be, and again, I still think that would have to be like a post-training thing, is because it has to learn to use which token. You know what I mean? Or it has to know when to generate those tokens. Um, beginning of thought, end of thought, which means it would still be in token space. Which is why I'm curious. Okay, let's just go for it. Let's just talk to David. Okay. Hello, David.
Hello there. How can I help you today?
So I'm trying to understand the coconut paper, without reading the whole thing word for word. Um, let's start. We'll close in on things eventually. Check on my battery. Okay. We'll close in on things eventually. Let's look at the diagram. I think you can see the current page I'm on. I want to understand the diagram I'm looking at. Is the BOT and the EOT. Is this like coconut chain of thought thing a post-training solution? Because from what I'm imagining is they have the dedicated BOT and EOT tokens, which means that the model is still going to reason in token space even. You know what I mean? Like everything is still going to be mapped to tokens, but it's just going to be their vector representation, and that the fine tuning will be sort of done on the what's it called? Just those outputs, in contrast to normal chain of thought where you're fine tuning or reinforcing good chains of thought. You know what I mean? Is so continuous chain of thought is going to structurally have the model think before it delivers its output, and then it's going to just do normal, what's it called? I don't know, normal loss on that output. Whereas chain of thought is more so post training of like, what's it called? More so post training of like, just using the fundamental idea of that better responses are probably followed by chains of thought. So what if instead of, you know, doing reinforcement learning on traces, on quality traces of thought, instead just like, you know, let the model choose how it thinks and perform loss on whatever, you know, it doesn't matter how the model thinks in the end, it matters the output. You judge the output, and then, you know, Coconut me lets the model think however it pleases in its ambiguous um, vector space.
The diagram on page 2 illustrates how Coconut differs from traditional chain of thought, CEOT. In CEOT, reasoning is expressed as a sequence of word tokens. Coconut, however, uses the last hidden state as a continuous thought, feeding it back as the next input embedding. This allows reasoning in a latent space rather than language space. Coconut isn't just a post-training solution. It involves a structural change where reasoning happens in a continuous space, allowing the model to explore multiple reasoning paths simultaneously. The BOT and EOT tokens mark the beginning and end of this latent reasoning mode. The model still uses
Wait,
tokens, but the reasoning process.
I'm a bit confused. By hidden states, are we referring to the outputs? Say that the downstream of a transformer is still going to be in token vector space. Are we going to use those as how, yeah, are we going to include those in our sequence for our next generation? That doesn't fully make sense. What do you mean when you're saying that hidden states are going to be used as input embeddings?
That's a great question, and it gets to the core of what makes Coconut different. In a traditional LLM, after the transformer processes the input and generates hidden states, a language model head converts those hidden states into probabilities over the vocabulary to predict the next word token. That predicted token is then embedded and fed back into the model for the next step. In Coconut, when the model is in its latent mode, which is signaled by the BOT and EOT tokens, it skips that step of converting the hidden state into a discrete word token. Instead, the last hidden state itself, which is a continuous vector representation, is directly used as the input embedding for the very next step. So it's not being mapped to a token and then re-embedded. The
Well,
continuous.
okay. So then let me push back on this. Is that difference, I would argue, is only significant if the vector embedding for tokens is different for inputs versus outputs. Is you're sort of saying is there's some sequence and then it's going to output into its output embedding space, and you're going to take that output embedded and going to put that as input, but you know you're going to skip the mapping part in terms from the vocabulary set, but it's still going to be the same, I don't know, arbitrarily 758D vector shape, but you're just going to, you know, you're still going to append it to the front, and those are still generated, and they could have been turned into tokens. That's sort of part of why I'm like pushing back is those embeddings could have been turned into tokens, but what's changing is once you turn them into tokens, you then again are going to do another transformation where that output token gets turned into the input embedding dimension. So if the input embedding dimension or the input vector representation for a token was the same as the output vector representation of that token across all tokens, of course, then we would it wouldn't be that much different from normal chain of thought.
You're right in pointing out that if the input and output embeddings were identical, the difference might seem less significant. However, the key distinction with Coconut is that it bypasses the tokenization step entirely during the latent reasoning phase. Instead of converting hidden states into discrete tokens and then back into embeddings, Coconut directly uses the continuous hidden states as input embeddings. This allows the model to maintain richer, more nuanced representations without the constraints of tokenization.
Okay.
It enables
So, okay, but this is still where I'm confused. So if you're not even going to use the token embedding representation, then what does how do I say? What are you referring to as the hidden states? Is like, you have a model that's made up of three transformers. Are you going to use the hidden outputs for each transformer step and feed that back in? And in what order or what structure are you going to do that? That's part of what doesn't make sense to me right now.
In Coconut, the hidden state refers to the output of the last layer of the transformer before it would typically be converted into a token probability distribution. Instead of converting this into a token, Coconut uses this continuous vector directly as the next input embedding. So during the latent reasoning phase, the model takes the final hidden state from the previous step and feeds it back as the input for the next step. This process allows the model to explore reasoning paths without committing to specific tokens, maintaining a richer representation throughout the reasoning process.
I'm, and maybe I'm blanking on the actual structure of an LLM, but I don't understand. So that hidden state is an embedded representation of the token. And you said you're going to feed that back in, which is exactly how tokens normally work. And the difference with normal chain of thought is that when you do that, that same token is going to be transformed into a different embedding representation. You're instead saying to use the same representation. So how is that different from the fact that if the input and output embedding representations for tokens were the same, how would that be different from normal chain of thought, where there's just a dedicated, where there's still a dedicated begin of thought, end of thought?
In a typical LLM, the hidden state is transformed into a token, which is then re-embedded for the next input. Coconut skips this tokenization step entirely. Instead, it directly uses the hidden state as the next input embedding, maintaining the continuous representation. The difference lies in avoiding the discrete token step, allowing the model to explore
Okay,
multiple.
so once again, but in comparison to chain of thought, Coconut's value isn't a speed sort of thing in terms of skipping that tokenization. You know what I mean? The If the input and output embedding representations were the same, then that, even if you did normal chain of thought, those two transformations would be the same as exactly taking the same vector representation, because the mapping would effectively be an identity mapping. It would be an inverse.
You're right that if input and output embeddings were identical, the transformation would be like an identity mapping. However, Coconut's value isn't just about speed or skipping steps. It's about maintaining richer, continuous representations that allow for more flexible reasoning paths. By avoiding tokenization, Coconut can explore multiple possibilities simultaneously, which can enhance reasoning capabilities beyond what
You're not
discrete.
you're not answering my question though, because it's still existing in the same space. All right, we're gonna put a hold on that. Is what's it called? And I also don't want to spend too long doing this. Let's see. But those are sort of like, the centers of like my conversations. Is like, I think I that one may have been a failure. I don't know. It's hard to tell, man. Um, let's see. So that's Gemini 2.5 Flash. Can you give me a better answer, please? So maybe Opus will do a better job. Let's do this. Oh, I'm hoping LM head stands for linear mapping head desperately. And then Logits is going to do softmax. Argmax slash sample. Sample, hopefully, you sample from the distribution, or argmax would be selecting the index for which the softmax distribution is maxed. Okay, I think that's okay. You get a token ID from that. Oh, I don't like that. Embedding table. Oh, but embedding table is when you put it, is the input embedding table. Okay, your sharp observation, whatever, is the LM head and the embedding table were exact inverses of each other, an identity round trip, the normal chain of thought would be already doing the same thing. It's the RMX, not the space. So the thing that changes. Oh. Okay, so let me speak this out loud. I don't have it fully yet, but let me see, let me speak out loud what I'm thinking. Whatever. Um, is so I'm right to point out what I was pointing out, but Claude is arguing that the fact that Coconut doesn't do an argmax step for choosing the token, but then I'm confused because then what token? What token are you going to send back? Interesting. What if they did like a weighted average token? You know what I mean? Doesn't make sense. Um, is the entire continuous vector not its nearest token approximation? No argmax. No argmax. Hmm. Okay. The difference is not the vector space. It's that normal chain of thought round trips every step through a non-invertible argmax. Has the full hidden state. the full hidden state of the next token. So I'm still a bit confused. So we're not doing Armax. When you, oh boy, okay. So when you map into, let's see, you have a sum, you have an n, unknown n, capital N, by 768D. Yeah, it's not a square matrix. And you're going to get the next token. You're going to get the mapping for the next token. LM head is the output, and so, sorry, I'm not the fastest typer. Let's see. Hidden state of the next token. Careful. Okay. Last hidden state. The hidden state isn't of the next token. It's the model's processed representation at the current position. And it's its job to predict the next token. So at position T, after running all the transformer layers, you get one vector. Correct. I agree with that. That HT is the output of the last transformer layer at position T. I agree with that. And the thing, and it's what? And it's the thing that knows what should come next. Okay. Everything below is what you should do with H. The normal forward pass is say D is yeah. Normal generation of stuff. LM head, the linear mapping from hidden space to vocab space. Interesting. So that, and that's, as sort of like context, like, if this is how like researchers are talking about these things, this isn't how I talk about it. I've never thought about like, you know, that your last transformer embedded space linear map wise contains information of what the next token should be. You know? JD linear map. Oh. Oh. Wait. Yeah, is that why that's why it's lossy? Is you're going to do a linear mapping of this hidden representation of what the next vector should be, but by forcing it to be some sort of linear transformation. Wait. Z, yeah, is you're going to transform that information, that rich information that contains what the next token should be. You're going to perform a linear transformation such that you get a vector that represents the probabilities for each one, and then you don't exactly argmax it. Z and V argmax or sampling. Wait, I'm close. I think I'm close. Wait. So H of T is being forced to map to vocab space. H T H of T is now. No, okay, you don't do argmax. You do argmax sample or softmax. Okay. Oh my goodness. How would you spell loosely? Oof. Okay. I don't know when the last time I spoke out loud was. Okay. Sorry, I can't spell. Balder-rich information is loosely related to no, it's lossly. It's lossy. Okay. But the um information is loss illy. Whatever, bro. Oh my goodness. Is lossily forced into a linear transformation. Like it shouldn't be a linear. You have all this information over what the next token should be. Like it shouldn't be forced to choose the next token. Yeah, I actually do like this idea. It shouldn't be forced. Okay. But yeah, okay. And maybe this is me learning. Okay. So, okay. So softmax is going to be across Z of T. And for whatever reason, we have H of T. We've done all these transformations and we have this rich vector representation of what the next token should be. And for whatever reason, we're going to force that to be multiplied by a matrix WLM. And that resulting vector is going to be values over relatively which actual token we should choose to represent that as. And that is lossly. That's like poor, you know? That's not how you would think about that. You know what I mean? Like H of T is rich, but we're saying it has to be one of these, you know? And like, yeah, so like WLM is like learned, and we have like, you know, loss and all that kind of stuff to make it like decent, and it works. But just that's a poor way to manage your information. Okay, softmax turns into a distribution. Argmax or sample chooses one from that distribution. Perfect. And so what dimension space is it in? So, okay. hmm And h of t is the same as token coconut design. I'm curious about that. Yeah. I think it's the same in a normal LLM. Yeah. In a standard transformer. Okay. Okay. Okay, we learned. Okay. So, what's it called? I'm pretty sure I ordered Uber. So my food might be here. So I actually learned something. What's it called? I'm gonna say it out loud and then end. We didn't do the goal at all. Let's see. Control Shift F. Um, how would I do this? That's like the first step. Okay. We can call that the checkpoint. We did goal 2 before goal 1. Let's see, what time is it? I don't know how long this video's been going. Oh my goodness, energy saver already? Guys, I'm hungry. Okay. So the video would be probably 30 minutes now. Um I gotta do the second thing. Maybe I turn it into 2 videos. Okay. Okay. I'm gonna eat. We're gonna do a second video. Um so yeah. Okay. Okay. So I think I had fun. That was nice. That was like, you know what? That was like 30 minutes of thought, you know. Hopefully again 30 minutes. And I think I understand the lever of coconut and why it's cool. And that worked. I like that. It started. And so like what was like yeah, let's assess if like Vault Chat is actually being useful. That was like 30 minutes. 30 minutes in comparison to me reading the paper. I don't know. I would have to sort of like read the paper and find out if I would internalize it that much in 30 minutes. But my understanding now is still high level. It's not it's not that nitty-gritty low level, but it makes sense. Is what's it called? By design, you have the hidden state after all your transformations of what's it called? And it's just in the token space. It's not the token. It's the it's the information that's been transformed because you have the sequence and you have everything here and you've put it through the transformers. And if we have a single sequence and our batch size is 1, we have sequence length, um, batch size, and what's it called? D model, and we're not worried about attention heads, right? Because it would be the what's it called? It'd be the size. If you had 4, it would be you just have a dimension for each part of attention or each head of attention. So we have in our trivial LLM, we have our 3 dimensions. We're doing batch size of 1, so we are going to predict a single token, and that what's it called? Yeah, after all the transformations, we've let it down attention, and h of t is a token space embedding, is a D model representation. Oh, oh, oh. That's why it's different. Is it's not really an embedding of the token, but it's in the same space because of the way the same dimensions, the number of dimensions, whatever, just because of the way we've done our transformations. I don't know how true that is. But okay, we learned. Um, and instead of doing blah 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 blah, we're going to take h of t, and that's where we're going to feed back in without doing any argmax, blah 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 blah. What is still open to me is when we choose the beginning of thought and end of thought type of thing. Is well, you could do that endlessly, you know. So at what point are you going to choose an actual token? Um, but I think I learned. I think that's good. I'm gonna get a snack break, and I'm gonna go for part two. We're not gonna spend all. I'm not gonna spend like all today looking at the coconut paper. Part two, I'm going to actually look into the the reproduction, the experiment, and what went wrong. And maybe probably not, but maybe understanding coconut better just brings me into doing that better. Okay, I'll see you.